This presentation will provide an overview of an innovative method for addressing the remediation of a common emerging contaminant. In particular, the presenters noted on this slide will describe sonochemical degradation, PFAS.
This presentation is on the sonochemical degradation of PFAS. In this presentation, I'm going to look at some of the challenges that are posed by PFAS contamination, how sonochemical methods can be used to solve some of the unique challenges associated with PFAS remediation, and how sonochemical methods can go about solving some of those challenges. Problems posed by PFAS contamination can be put into two broad categories: environmental challenges and health challenges. Environmental challenges include persistence. This is why PFAS are sometimes referred to as forever chemicals. Once you introduce them into an environment, they tend to stay there for a protracted period of time. They also can bioaccumulate. They bioaccumulate because of their persistence. Once you start introducing them into an environment or system, they tend to build up until they get to toxic level. They are also widely spread. They are widely spread because of their wild use in various industries and products. Health challenges include cancer. Once PFAS is introduced into the body, they tend to build up to toxic level and can result in various forms of cancer in our. In addition to the cancer that I made mention of in the previous slide, PFAS also affect our immune system. Once it is introduced into our body, it tends to compromise our immune system and making us less resistant to diseases, and can also make vaccine less effective in our body. It also affects our development. This is particularly associated with children. When pregnant women are exposed to PFAS contamination, they tend to give birth to low weight children, and also those children can have delay in development. PFAS also can affect our hormone distribution, in the sense that once PFAS is introduced into our body, it tends to affect our metabolic processes, which eventually affect our hormone production. PFAS also can affect our liver, because when PFAS get to toxic level, it can be dangerous to our liver.
PFAS remediation strategies aim to either remove them from the environment or break them down into less harmful substances. PFAS removal typically relies on immobilization and separation techniques. Immobilization is a straightforward and cost-effective method, which is why it's the leading approach in managing PFAS contamination. It focuses on keeping PFAS compounds in the soil, stopping them from leaching into the groundwater by binding them to sorbents like activated carbon. Separation techniques like soil washing involve using water or a chemical solution to wash PFAS from the contaminated soil. Phytoremediation is another natural separation alternative where plants are used to absorb the PFAS compounds.
Here I am looking at some of the unique problems that sonochemical degradation solve when it comes to PFAS remediation. Some of the existing challenges with PFAS remediation are incomplete destruction of PFAS, especially if you are using methods like carbon absorption. High energy demand is another challenge that is posed in PFAS degradation if you are dealing with other thermal methods, and also lack of versatility when you are dealing with methods like ISCO that can only handle PFAS in groundwater. Sonochemical methods solve the problem of incomplete PFAS destruction by offering a complete destruction option. This is achieved through ultrasound-induced chemical reactions, which are capable of producing reactive radicals that can attack the carbon-fluorine bonds in PFAS and then break them down into less harmful substances such as water and carbon dioxide. Sonochemical methods also offer energy efficiency in PFAS remediation because they tend to localize energy in areas where high energy is needed for PFAS destruction instead of distributing high energy across the system. It also offers versatility because it can be used in both groundwater and wastewater remediation. Thank you.
Sonolysis is a cutting-edge remediation method that uses ultrasound to generate gas bubbles in liquids. When these bubbles collapse, they can create extreme conditions with temperatures up to 10,000 Kelvin and pressures of hundreds of atmospheres, forming a reaction hotspot. This falls under advanced oxidization process, and this process begins with high frequency ultrasound, producing alternating pressures in a liquid or a slurry, growing and forming bubbles. And when these bubbles eventually implode, they release energy that creates hydroxy radicals capable of advanced oxidization. Sonochemistry operates at three major key sites: the bulk solution, the gas interface, and the bubbles interior. PFAS molecules, due to their hydrophobic nature, migrate into the gas-liquid interface, where radicals attack and degrade the molecules, and the products of this breakdown are usually sulfates, fluorine, hydrogen ions, carbon dioxide, and this precise method makes sonolysis very effective at approaching persistent compounds like PFAS. Ultrasound reactors are built with three major components: a generator, a transducer, and an emitter, with sometimes some boosters. The generator creates an electrical signal, which the transducer then converts to ultrasonic vibrations, and the emitter amplifies these vibrations and transmits them straight into our solution, so our liquids or slurries. Cavitation is often uneven within the solution, and it can create areas of high and low activity. And to address this, advanced reactor designs incorporate tubular or hexagonal geometries with multiple different transducers to ensure a more even cavitation. This configuration enhances the efficiency of ultrasonic energy distribution, creating the necessary conditions for PFAS degradation.
PFAS is an expensive problem. A 2024 paper by Dr. Alison Ling evaluated the theoretical cost of PFAS remediation based on current emission rates and estimated remediation costs. The key outcome was that there is not enough money in the world to remove PFAS from the environment as fast as we are adding it right now. PFAS remediation and destruction costs are currently difficult to accurately estimate given the complexity of PFAS, limited scalable PFAS destruction technology options, and the lack of published field-scale studies that include financial analysis. Although there are limitations in Dr. Ling's cost estimates, the study effectively advocated that we need both policy-level changes to control the production of PFAS and cost-effective remediation solutions. Engineered PFAS destruction, which includes sonochemical degradation, is more costly than the commonly applied absorption technologies such as granular activated carbon that effectively remove but do not destroy PFAS from solution. PFAS degradation costs using sonochemical technologies are not currently available. Instead, we reviewed the sonochemical degradation costs from a 2010 study for other contaminants, including phenol, reactive azo dye, and trichloroethylene. This provides us with a high-level understanding of the potential economics for treating PFAS in wastewater via sonochemical technology. The costs for degrading these contaminants were wide-ranging. The capital cost ranged from 30 million US to 20 billion US, whereas the operating and maintenance costs range from 1 million US per year to 653 million per year. It's evident from these wide-ranging capital and OEM costs noted on the slide that sonochemical degradation is likely to be cost prohibitive without significant advancements. The costs in the previous slide translate to a PFAS treatment cost per cubic meter of between $6.8 per cubic meter to $4,104 per cubic meter in Table 1, which is far too expensive for practical applications. This technology is unlikely to proceed as a sole PFAS treatment option. Sonochemical technologies may instead be more cost-effective and environmentally sustainable as a part of a treatment train where other technologies pre-concentrate the PFAS, which can then be destroyed via sonochemical methods. Overall, we need additional bench and field scale research to better understand the potential costs and scalability of this technology.
One of the key advantages of degradation over immobilization and separation techniques is that it doesn't generate hazardous waste like sorbents or plants that require disposal. The process creates high temperatures and reactive species, such as hydroxyl radicals, which break down PFAS compounds. This makes the process environmentally friendly as it doesn't rely on the addition of external reagents, and it minimizes the need for waste management. Sonochemical degradation is also more energy efficient compared to high energy techniques like incineration or ball milling, which require significantly more energy to generate the high temperatures needed for effective PFAS degradation. The energy efficiency of the process is also enhanced by its simplicity, making it ideal for point-of-use systems such as under-the-sink installations, where only the water being used is treated. Sonochemical degradation is still in its early stages of development, and it faces several limitations before it can be scaled up for commercial application. Firstly, the process may disrupt microbial ecosystems by degrading the beneficial non-PFAS organic compounds. Also, an incomplete breakdown of long-chain PFAS compounds would lead to an increase of short-chain PFAS compounds that require further treatment. Unfortunately, short-chain PFAS compounds are hydrophilic in nature, unlike their hydrophobic long-chain counterparts. This property makes them less likely to reside within the cavitation bubble where they can be degraded, or at the liquid-gas interface where reactive species can break them down. In situ soil remediation is also not feasible since ultrasound waves require a liquid medium to generate cavitation bubbles. This means that contaminated soil must first be turned into slurries. But the downside is that sand-sized particles in slurries can absorb or reflect ultrasound waves, which reduces the effectiveness of the process. Scale-up challenges also exist, as most studies have been conducted at bench scale, which may not reflect real-world conditions. Additional research is also needed to scale up reactors for the treatment of larger volumes of contaminated surface or groundwater. Finally, current PFAS treatment studies rely on arbitrary benchmarks due to the absence of official PFAS standards. In the future, this could impact the remediation of sensitive sites that require more conservative site-specific standards.
Based transducers based on batch reactors struggle with heat, energy, and dissipation when on a larger scale. When alternative approaches use continuous reactors with tubular or hexagonal designs, such as the one on my slide, and multiple transducers, enhancing the cavitation efficiency and making sure the whole solution is homogeneous. Combining sonolysis with additives like persulfate, hydrogen peroxide, or Fenton's reagent generates more radicals, accelerating PFAS degradation and reducing the energy consumed. And these integrations represent a promising path for maybe scalability and efficiency of PFAS remediation, so less energy needs to be used and essentially less cost.
In conclusion, PFAS compounds are emerging, widespread contaminants with complex properties that require specialized remediation. Common PFAS technologies concentrate PFAS, but do not degrade the compound. This contrasts with sonochemical degradation, that is an innovative alternative that is effective at breaking down PFAS compounds. Costs for sonochemical degradation of PFAS are not yet available, but costs for other compounds suggest the technology is not yet competitive for wide-scale implementation. This technology may be best suited as the final step as a part of a treatment train. And finally, bench scale studies show promise, but further research is needed to scale up for real-world applications.